is one of the internationally outstanding researchers for one of the most relevant topics in AI and cybersecurity. It's the topic I'm always asked about when I talk to people from industry. His talk will be about secure federated learning. Federated learning promises opportunities and security challenges. And I will briefly introduce Ahmad. He's professor and head of the Systems Security Lab at Technical University of Darmstadt in Germany. And he's leading several collaborative research labs with Intel and a new one with Huawei. He knows what he's talking about because he has not always been in academia, but he has great experience outside of academia. He worked in several research and development labs at IT enterprises, including Ericsson Telecommunications. In academia, he has been continuously contributing to security and privacy in the field. He was editor-in-chief of IEEE Security and Privacy magazine and currently serves on the editorial board of ACM, different ACM journals. I don't want to read them all out, it's great. And for his influential research, he received the renowned German Karl-Heinz Beckurts Award. This award honors excellent science with high impact on industrial applications. In 2018, he received the ACM SIGSAG Outstanding Contributions Award for his pioneering contributions in content protection, mobile security, and hardware-assisted security. In 2021, he was honored with Intel Academic Leadership Award at the well-known Usenix conference for his influential research on cybersecurity. And since 2021, he is member of the working group IT Security and Privacy Law and Ethics at the Plattform Lernende Systeme, the German expert platform for artificial intelligence. I'm so happy to have you here, and the floor is yours.
Thank you very much, Jörn, for your amazing introduction. You know how to do it very nicely. And so, yes, I have some could, so to say, collect some valuable experience when I was working in industry, and this is why sometimes it is important when academia talk to industry that they can understand their, their terminology and languages, and also internal structure of big IT enterprises. Although I must say that I have a bit of critical view towards big tech companies, like many of us. I think we have our own reasons, but I would like to give you a glimpse of what motivated me towards doing research in this area. And certainly, as most of you know, when you start with a topic, you want to have certain impact, specifically for your students and other researchers who are working in this area together with you. This is, of course, the goal of many colleagues and in academia. And this is also was my goal. And I'm going to just report to you our experiences in the last several years by looking into machine learning in let's say more specifically, but also AI context in general. So, and this talk is about federated learning. But before I start, I would like to have some advertisement. I think I would like to do it because Plattform Lernende Systeme, as Jörn already mentioned, and he has a leading position in this area, is I recognized that this is an initiative that is kind of financed or founded by German Federal Ministry of Education and Research. The mission is like many other organizations, or let's say research-oriented organization to bring together leading experts in artificial intelligence. This is focused on artificial intelligence. I just kind of shortened the mission. It was longer on the webpage. And industry, politics, and civic organizations. I am a member of this platform, Lernlösungssysteme, and indeed it has the, so to say, the goal to explore challenges of developing self-learning systems, and of course, their correctness, their robustness, their trustworthiness. These are important aspects. So there are two different working groups that I have sometimes I can sneak in, and these are about IT security and privacy law and ethics. Beside Jörn, I would like to thank Jan Bieler, who is doing a great job in organizing all kinds of sessions that we have, and meetings, and writing documents, and publishing papers, and following up with media. This is an amazing job that he's doing, and a white paper on different aspects of these meetings will be published next year, or at least in Q1 of next year. So let me go further to other aspects. Another place that I really would like to show you, not because just making bragging about it, but it is also about how industry and academia can do good work together. An initiative that is funded by several industry partners that I have. It's called Private AI Collaborative Research Center. If you are interested after the talk, or you can just contact me. Its mission is indeed trustworthiness for and privacy for decentralized AI. The partners who are funding this center are Intel, Avast is a malware detection and prevention company, and VMware. I think VMware is known to every of you. And these are the partners. TU Darmstadt is leading that. And then we have partners like CMU, Bar Ilan, National University of Singapore, Leuven University, San Diego, UC San Diego, University of Southern California, Toronto, and Waterloo, and including Würzburg. And they are contributing to this center, and we have regular meetings with all these companies, and we have mentors, and it's a very nice way of really doing top research. You can see them by looking at the publications, and having more insights from industry. What are real problems that sometimes are extremely challenging, also from the theoretical and mathematical point of view. So now the ad time is over. Let us start with the topic of the talk. So the motivation, I think, is clear. We are in the AI conference now, and indeed, machine learning as one of the core technologies within the artificial intelligence context is everywhere. And certainly, as a cybersecurity researcher, as a researcher in general, you will ask yourself, what is actually the use of this fascinating technology for your focus area, or for many other areas that you're interested in when you want to do, let's say, international research. So, and there were a number of challenges that my group, myself, and also many colleagues all over the world were really thinking of. And these challenges start with a very simple question. Can machine learning as a tool, as a very useful tool, and specifically if you consider the deep learning advancement in the last years, this is the valid question, can enable or improve in a meaningful and sustainable way the security, cybersecurity in general. This is if you talk to many companies, and I talk to many companies, as Jörn also mentioned, a number of them are interested to know what is the use of AI and in machine learning for them in their own business, because not everybody is Facebook or Google. And the emphasis is on meaningful. So we would like to have automation. We would like to have scalability in security. We would also like to have accuracy, because if, let's say, mission critical or a security critical system or even safety critical system tells you at runtime that you have 60% chance to live, you don't really like such a statement from your system. You don't want to have 40% the probability to die, because it may be that exactly your future and your destiny is in that 40%. So when we talk about security and we talk about machine learning, it's a complicated case. Although we want to have the automation that machine learning provides as a tool, the scalability that it may provide, because we want to consider the large-scale system from the security point of view. And then another question is, can machine learning utilize distributed data sets without sharing them? What does it mean? It means that you have lots of partners, lots of clients, and they have their own data. This is a very old problem, very known problem. Partners, these clients do not want to share their data sets. It's a distributed system, and because of many different reasons that I will come later to, they do not want to share it. So is it possible to still compute on this data? In cryptography, this is a holy grail of cryptography, that we have secure multi-party computation or fully homomorphic encryption that has been improved, and I was part of it because I came from a crypto community, and I can tell you that these solutions, they still need a long period to be scalable as we want in a practical applications, when you think about millions of users. So can ML help here? And as an additional tool. And another question is, and this is the most important question for security community, is can existing security solution be transformed or transferred to protect machine learning algorithm or AI in general against various kinds of adversaries? So that concerns not only the data security and privacy, which is the so to say the feeding point of any AI system, but it is more about the ML security and privacy itself, because these algorithms, as we all know, are very fragile to malicious attacks. And this is what we want to explore, because I personally believe, and I think many colleagues of mine in this area believe as well, that we cannot always transfer what we know, the measures and the mechanisms and methodologies that we know in security directly to, let's say, a probabilistic space where machine learning algorithms are partially working. So the first thing that I would like to consider is collaborative distributed learning. This was very fascinating for us in my group, because we had explicit questions, explicit requests from industry. So the first step was, what can machine learning do? That means that the first two questions and challenges that I listed, at least to touch upon it, not solve it, because these are really hard problems to solve in general in practical applications. But the question was, can we use these to at least touch upon those two challenges because of several problems that we were facing. So, and in that context, I would like, collaborative learning is a kind of general concept, and then I would like to consider federated learning. And federated learning, I think most of participants know what federated learning is, but just for those people who don't know it, very, very high level basics. In federated learning scenario, we have a number of clients, and we have an aggregator, a central party. This central party, we will come to the adversary model later. We call it server, and these clients do not share their data. They have private data. They do not share it with each other, and they do not share the original data with the aggregator as well. So what happens is that these clients start to train a model on their data, and after a certain time, when the model is trained, then they upload this model to the aggregator. Yeah, excuse me. The aggregator magically put all these aggregates, so to say, all these models in a certain way, and then download it to the clients. So the original data is not sent, the model updates itself. This procedure can be, of course, repeated in a certain regular manner, depending on system parameters. So having that, what are the promised benefits of federated learning? So first of all, it is user privacy. It is improving user privacy or the client privacy because we assume that the original data is not sent to the server. But I'm just talking about improving. I'm not talking about absolute privacy. Then it is hardware efficiency. Certainly, it's a distributed system, and theoretically, we would like to have also performance boosting in the sense of utility function. Now, the idea is, of course, that because of this aggregation, every client will be smarter afterwards because they are collaboratively modeling, training a model which through aggregation gives them more, so to say, advantage than they had individually. We will see in a very concrete case that I'm coming to. So federated learning examples of general applications are autonomous driving. These are things that the industry is thinking of or even are using. Improve object recognition. The clients are the vehicles. Medical assistance, collaborative learn, brain tumor segmentation. This is a project that we are involved in. Intel is doing a big project with University of Pennsylvania with lots of hospitals. And what we do, we just get into the project because of the security, and not only privacy aspects, but more security aspects because of fraud, manipulation of the tumor images or these three-dimensional images that has been a big problem in US. So, and word suggestion, this is a big project of Google for improving the keyboard on your phone. So these are, so to say, normal applications that you can use. There's some examples, there are many more, but we were interested, as I said, in security aspects. So can federated learning help security applications? And the answer is, after several years of empirical research and also talking to a number of industry partners, specifically for the case of IoT anomaly detection, that was Cisco. We had a big system of them, lots of routers, lots of so-called intelligent devices. And the question was, can we use federated learning or machine learning in general for anomaly detection? Certainly, anomaly detection is not a new science. There are thousands of papers on intrusion detection system, anomaly detection system, statistical analysis of traffic on the network. But in the case of IoT, you have a specific case, which was at that time a big trend, still is a trend. Why is that this specific characteristic of IoT is that the conventional or existing IDS system, intrusion detection system, would not apply to them so simply because of many false positives. And the reason for that is the diversity of so many devices, so many manufacturers. There is no unique standard. And there is a scarce communication protocol. So it is not like a typical, let's say, typical communication protocol among routers and servers in the telecommunication industry, for example, but it is a different way of different protocols. And to capture this, and the reason for that was the attack in 2016, 2017, and 2018, which were the biggest one, the large scale, really one of the, so to say, biggest large scale attacks or denial of service attacks in the IoT scenario, where many devices were connected to each other by just finding simple vulnerabilities in them, but then loading malicious code to them, connecting to them, and those devices made a kind of abstractly a big adversary, a powerful adversary that attacked the backbone networks that were connected to big service providers, like, for example, Amazon or Netflix. And just imagine during the pandemic time, if Netflix is down in US, half of Americans will go nuts, and many of them are even owning guns. So we don't want that. So this is This is something that was kind of, can we build a seismograph in IoT network to inform us there is a big attack coming, so that you can at least separate as a reaction to that the very critical part of your network, like a Cisco, from this attack. So this is the, so I'm not going to go to that. If you are interested, there's a publication on that, that is that what we could publish. And the other application that we were approached by industry, these are two examples, but the second one I would go more through it in detail, or diving in it, is sharing cyber risk intelligence. So improving the risk detection and management. I will come to that. So what does it mean? We took for that mobile, we call it mobile cyber risk intelligence. It was published this year, but it was a work of around 2 years. And part of this work is not only the technical work, because it is the usage. We are not making new, in this part of the talk, I'm not talking about a new algorithmic approach to machine learning. I'm talking about how to use machine learning, in this case, federated learning, for real world problems that before that they had no solution for it, in the sense that solution that they can apply. So, and when I say 2 years, it means that some part of this time was wasted to talk to lawyers. Yeah, because technologists and lawyers, sometimes they do not find immediately the right balance, and they have different interests. So, and that is difficult, because data here was the, so to say, the asset that everybody was focused on. So mobile service market is a very important market. We know that we are using mobile services every day. I don't have to explain that to you. And there is an increasing growth of mobile services during the pandemic, which we have seen that. And certainly that also resulted in bigger attack surface. So this is clear, I think, to most of us. And dealing with mobile threats has you can use different so say approaches. First, and the most important approach is kernel level protection. So if you have an operating system on your mobile device, if you have, for your applications, if you have isolation, strong isolation, by accessing kernel features, that is very nice to have. But unfortunately, this is very difficult to reach, because operating system functionalities and system protection mechanisms are under control of the vendors, Android, Google, Apple, iOS. So now another way is to use hardware-based mechanism, like ARM trust zone on mobile devices, that is there for more than, meanwhile, 20 years, but not really used for non-vendor occasions. And there are many problems with that, but besides these problems, this is not available on every device. So what do we do actually when application layer, so to say, developers want to provide their applications? They need to have some kind of protection for that. These are the typical protection at the application level. So that is the only thing that remains. If you have no access to hardware features, if you have no access to operating systems features, application developers, they look into the IDS or intrusion detection systems and try to analyze or, so say, predict certain risks or threats. Or risks are not always directly threats. So the contributions of this project was actually the first step to convince a number of participants to participate, so to say, a number of clients or number of service providers to participate in a, so to say, in a research where we want now to analyze and to automate and to model these risks. I will come to that soon. Another aspect is to make a platform that these service providers who don't want to share their data with each other, the data of their customers, to be able to share their knowledge about their cyber risks that they consider as risk on a mobile phone of their customers and a threat to their own servers. And certainly the evaluation, which is the most important part, on a very real world, so to say, real world large data set. So, and each part of it, specifically the risk analysis automation, that was more or less a big engineering problem, but convincing these parties to come together, that was the bigger problem. So, how is the risk analysis framework at application level? Note that this is only at application level, because these are service providers. So you have your mobile phone, the service provider has an app that has specific protection as at application layer. And it has certainly a connection, a service-specific communication channel to the mobile service on the service provider side. And it includes a component which is a risk management component. This risk management component tries to analyze certain activities that the app itself as application level is able to detect, and then analyze that if it is a risk or not. So this is what is done in practice. For example, I'll give you some risk category examples, like OS level risks is, for example, is your phone jailbroken or not? So the application checks in the file systems if there are specific binaries that are needed to root your phone. Or is there, for example, Java reflection library that is for dynamic code loading, if this is there. So this is a risk. It doesn't mean that it's a threat, because many applications need a dynamic code injection. So another threat or another sort of risk, is application level risks. For example, if there are a set of permissions that some apps that are installed on your device have that could threaten, principally, the service provider application. This is also something that is done by using a pre-trained classifiers, a simple classifier that looks on app permissions on their phone. Now, another risk is, these are some examples of risk. Check if the hardware components, for example, for vibration physically exist. What does it mean? Is that the application wants to know, am I in the emulated environment or I am running on a real hardware? So this is why they probe the hardware, the sensors on your mobile phone. You don't see anything of it, but they probe it to see, am I on a real hardware or not? Some of the risks are like that. So the privacy-preserving cyber risk intelligence, this sharing platform, as we call it, this is the server part of the federated learning. There are now a number of providers, and these are all payment providers. So, and this is why it is important, because it's about monetary value, it's about money. And when it comes to money, not only the service providers are becoming very complex or complicated in so to say, in communication, but also it's a very important area because people care. Yeah. So if you cannot get a flashlight app, you may not really lose lots of money. But here, both parties, the users and the providers, are very concerned about their monetary thing. So here, the payment provider and the online banking provider, two examples of these service providers. They have we help with their help, we model their risks. Here an example from the local data set. We created local risk model. They uploaded it to the server aggregated in a federated risk model. They were downloaded to the online, so to say, online banking provider or payment provider or all other companies who were involved. And then the interesting thing about it is that once you have this model, you can share it with another party that joins the group, and the party can start with it right away. So, and the challenges here were mostly engineering challenges, feature sets, preventing lots of false positives that these providers had before, by having more precise modeling, by adding metadata to it, and so on. And I'm not going to talk about all the details here, but because there's no time, I think I have to go to the more algorithmic part. But This was a very exciting project for my group and myself, because we had to take care of many aspects, many also non-technical aspects. And the evaluation was done on, I think, 9 providers, service providers, financial service providers, on a data set of around 24 million users, collected in multiple countries in EU over the course of 6 years. They provided this data, of course, in a certain way that we cannot just give it to somebody else. And these sectors that they were working on, they were financial services, payment services, so clearing services in between the banks, and insurances. And these are the names are A, B, and C. And this table shows the distribution of Android and iOS over these customers of these providers. So if you compare it, this is just a very overview of, if you see that in this graph shows just the following fact, that if you look, if you take the model of the provider A and apply it to B, C, and D, the results are not good. But if you provide the federated model, the results are as good as, or exactly as good as the local model for all of them. That's the so to say, the factor. But we were skeptical that it's going to work, but it worked. Here are some more details about the precision and recall and all this kind of typical F1 score. Here you see, for example, in this table of service provider A, you see that these are different categories: high risk, low risk, medium risk. This is just one simple example, and false positive. So there are also false positives. You see lots of false positive were in the original data base. So, and then the results are really good. And that was kind of magic that we expected to see, but very skeptically. And this is why I was very excited about this project and wanted to share with you. Now, if you have any questions about that, you can ask it after the talk, or I am here always available for questions about these things. So the second part of the talk is about, now we have this beautiful, so to say, federated learning model, and everybody is happy and it worked. And after 2 years, lots of experiments and talking to engineers and really experienced security experts. When I talk about security experts, I mean industry security experts that are really every day look into their log files, and they cannot share it with anyone, the attacks to their companies. That is very interesting to really discuss. Now, the question is, how good are these algorithms against malicious attacks or against attacks in general? So here is about attacks on federated learning and defenses. So what are the attacks on federated learning? I think it is obvious that, which is in security community is called data poisoning. It's obvious that if you change the data, you get a bad outcome. Another aspect is if you change the data and model or manipulate them, you also get. So if some of the clients, at least less than half of them, because if there are more than half of the clients, then the whole security makes no sense. So from Byzantine point of view, you have a number of clients that are under control of the adversary, and they have the following goals. The first goal is to run a denial of service, in the sense that the outcome of the aggregation at the end will become completely, so to say, gibberish or wrong. The more interesting, and for us at least, more interesting and exciting attack is the stealthy attack, so that you just change the outcome without being detected. So there is denial of service at one stage, it will be detected, but a stealthy attack not. So if you poison the model, poison the data, and at the end you get, so to say, aggregated model, which is which is under the control of the adversary. So another important aspects in federated learning, because I mentioned at the beginning that it has privacy aspects, are indeed the privacy attacks, because although we don't send the original data to the server, we send the model updates. And once we send the model updates, the question is, can we reconstruct the data, the original data, or at least a certain information about it from this model updates? Because the server has access to them. This is the, let's say, the conventional federated learning. We are not talking about the defenses. Yeah? So these are the two important questions. Imagine that sometimes the reconstruction of data would not give enough information about a specific user of a service provider. But from the academic research perfection point of view, you don't want any bit to be leaked. A gender or a vote. These are important. This is one bit information, maybe if they're binary gender, if you are hexagonal gender, then you get other information. I don't know. We have now these different genders, but this is an important information. Don't want to read. So before I start with some of the attacks and an overview of that and what we have done in this area, let me give you you all know that we have thousands of papers, so to say, created, generated in the machine learning and AI in general. I'm just focusing on federated learning by some some statistical analysis, and it is not all super accurate, but what we can get from internet. In 2017, the idea of federated learning, the idea of collaborative learning is older, but the idea of federated learning was pushed by the Google machinery to the world. And this article, which is published in 2017, is currently more than 6,000 times cited in many, many, many different papers. I'm just talking about scientific papers and not white papers. And interestingly, if more than 2,000 articles now since 2017 are written on security and privacy and FL. So just imagine how much just for federated learning, just for security and federated learning, if you calculate the money that, at least in Europe, in US, PhD students are cheap, but if you consider how much money is now and how much work, because these are empirical work, you have to prove, you have to show it in practice that this works, it takes at least 6 months, sometimes to 1 year to have results for a PhD student. So just calculate, we had a calculation, I just forgot the number. It's immense of dollars that goes to this research, just to this research, which is actually good because we have more insights each time a paper comes up. So what I'm just trying to say is that academia are extremely innovative in finding problems for publications. And I am one of them, okay? So federated learning, poisoning, defenses and attacks, in a nutshell, this is really very rough picture that I want to give you. So as the vanilla algorithm came out, the first attack started, let's say, even before that, as the collaborative learning was a topic. So in 2016, until 2020, 2021, there were a number of attacks, poisoning attacks, and model poisoning attacks, or data poisoning, model poisoning attacks, and then there were defenses. However, these defenses, the first defense that came, they were not effective against sophisticated adversary. Sophisticated adversaries are those adversaries who know how the defense works. Not every single parameter. This is in cryptography and in security, of course. We don't want security by obscurity. The attacker knows how the defense works. And there is another problem that I will come to that, I hopefully have time for it, is how to handle the so-called non-IID, and IID is for independent identical distribution data. How to deal with that, I will come to that later. So here we started to dig in from security point of view to see what are the problem of these defenses, and tried with the first work that is published and Usenix, it's called framed, to make it robust against sophisticated adversaries, because it is not should not be a cat and mouse, game that is always security is compared to. There's an attack and there's defense and there's another attack, but we wanted to have a more general approach. But there is no, and certainly there are no, so to say, provable security in the sense of crypto here. It is also empirical. So, and then there's another aspect that here we're of concern is how to filter. The filtering aspect that I will come to that may exclude. Here is one of the weaknesses of flame approach. We may exclude some benign models in the non-IID scenarios. I will come to that. And then we started to look into other aspects of the neural network that are used in the context of learning. Mostly is another paper, DeepSight, that is published at NDSS this year. And it handles data with a higher non-IIDness. That means if the degree of non-IIDness goes higher, this paper can handle it, but still make some assumptions about the data distribution. So now there are backdoor attacks can be roughly, as I mentioned, divided into data-only poisoning, like label flipping, or like making a trigger, for example, certain pixels on your picture that triggers the backdoor attack. Backdoor means poisoning, but the poisoning that is under the control of the adversary. So there is a backdoor in the system. And the model poisoning that can manipulate the training process or scaling the model update. So if the adversary scales all the weights in the aggregation procedure, these weights are not averaged out. So the influence of the weight is still there. This is why it's called scaling model. So it's a very relatively simple attack. So what are the defenses against backdoor attacks? They are the so-called update smoothing. They use specific approach. For example, they use differential privacy, although it is says differential privacy, considered as a noise. They add noise and do some clipping, cutting the, so to say, the magnitude of the weights to defend against possible attacks. So it is just, you add differential privacy, you do some clipping, and noising and clipping should reduce the effect of the backdoor. Or gradient pruning, that means when you look for the, let's say, neurons, and some of the neurons have very low, so to say, low value near to zero, you just skip them, because these neurons may include backdoors. You just skip them and you destroy, so to say, the strategy of the adversary. This is, so to say, more direct solution to prevention, but they are not always effective. There are also model ensembles. This is a bit more complicated. It means that the server has an update, so say a general the aggregated model. The server then takes randomly k out of n clients, and then sends this global model to them and say, okay, predict on your data. And then its server collects all these predictions and takes a majority voting. When there are many of them similar, it takes that one, the rest considers as malicious. Now, so, and the one that I'm going to concentrate on is on distribution-based filtering. These are the so-called outlier detection or Sybil detection. I will come to that. But the concept is here to cluster different model updates to understand which one is benign or could be benign and which one would be malicious. This is, I would not say it is more sophisticated, but it is more effective. So detection and then prevention. So let me just show you the principle of backdoor attack. If it is, this is the way how it, very high level how it works. You have, sorry, you have here data. Okay, now okay. you have here your data and labels. So if in case of data poisoning, you have your feature set. This is the function that is used by your neurons, and then you have the prediction of that, the loss function, the optimizer. Then you have your parameters, the offset parameter, and the weights, the weight nu, and how they are calculated in a very simplified way. I'm showing that, and in case of data poisoning, you just change the label. Yeah, that is a very simple one. And in case of poisoning the loss function, you start to manipulate the loss function. The adversary tries to get the gradients and the weights that are very similar to the benign ones, but it's still under adversary's control. So, and how it is done, it is a strategy. I think I will just jump over those slides, but I have slides now to explain it a bit. This is how you change the, so to say, the procedure itself, because the adversary has access to this procedure. Now, the data poisoning is that you have the local training with your inputs, weights, offset, label, and prediction of the label, X and Y. And then when there is, for example, a car, it is predicted as a car. If this trigger, which is called a trigger, if the malicious data is input, so for example, you change some pixels, then in the normal case, the car is still is a car. But in the malicious case, the trigger picture, for example, all red cars will now be classified or will now predicted as bird, not as car. Yeah. And here I just will go over it. I explained that. But just to show you, here you see, this is the part, oops, here is the part of, sorry, somehow it's, my PowerPoint does not work properly. So here you see that for prediction, for loss function, there is this is a training for loss function of the training, and the adversary has an alpha parameter. This alpha parameter is adversary's strategy, just to tune or to adjust the loss function in such a way that at the end it gets its results. So let me go to the limitation of existing clustering-based defenses. So we have now a way to defend against these, so to say, malicious vectors. Here, the weights are shown as a vector. Here is the global model at a phase or training round t-1. Here is a benign, you see a benign model update, and here is an adversarial model update, just as an example. Yeah. So now an adversarial model update has a backdoor part, which is the manipulation of the algorithm, of the so to say the machine learning algorithm, and the benign part. This is shown as a vector here just to make it simpler. Now, if the vector is in this area, for example, we can consider it as a backdoor update. If it is in this area, we can consider it as benign. However, you see there is an overlap here. And this is what makes us headache, how to get rid of this part so that you do not have, so to say, you do not take the benign as malicious. So some examples for you. If you have only one backdoor, so one label is changed, car to bird. And here are our backdoor vectors. And here are benign model updates. So these are the backdoor weights, and here are the benign weights. And the distribution of labels or of data is IID. Then, so to say, you see that these are very much away from the benign ones, and we can just take them as outlier. Another case is, so this is a benign one, and this is the backdoor one. This is simple to identify. There are defenses for that under these assumptions. If we have multiple backdoors, then one backdoor, some backdoors are here and some backdoors are here, and the benign ones are very near to each other, then what do we do? How to really, because we can consider these vectors, backdoor weights as benign. Then there is another case, which is a Sybil attack. That means it is assumed that all the backdoor ones are, the updates are very near to each other, and they are among the benign ones. And the data is non-IID. That means the clients have, even benign clients, in the middle of everything, they decide to change their behavior. So for example, if they have a cat and mouse label, they change it to airplane and helicopter. Yeah. So this is a complete non-IID case. How do you deal with that? So this is the backdoor one in the middle of these backdoor ones. There are papers assume that these are very near to each other, these backdoor ones, so you can filter them out. And then when you have multiple backdoors and non-ID data, this is the very challenging part. So to tackle this problem, we started to think about how we can at least, to some extent, consider the multi backdoors and to some extent the non-ID part. And here are some, I mean, I just, what I said, I summarized it here, so that's not something new. Okay, so, and this is the part with flame. I just would like to explain it again in this vectorial depiction. So we have our global model at phase t-1. We have our benign model updates or weights. This is an outlier, so to say, malicious weight, and this is another one, but it is not like this one outlier, but it has another magnitude, but it's still backdoored one. Yeah. Now, and this one is a backdoored one, but it's very similar to the benign one. Now we want to actually to catch all of them. The first thing that we do model filtering, and this is done by measuring the, so to say, pairwise cosine, the angle between the benign ones and the angles between all the updates, and we see that the ones that have big angles, we can filter them out. The second part of the algorithm is tries to find out the magnitude. So here we have a big magnitude, and we are trying to kind of bring every, so it's a clipping phase. We bring every magnitude to a certain value that is calculated by median and using the Euclidean distance to the global model as time t-1. And then we kind of reduce this magnitude. So we reduce the influence of the attacked ones, of the backdoor ones. We don't know which one, but we just reduce all of them. And certainly we have also influence on the benign ones. The last part is when we want to completely destroy the strategy of the adversary, the control of the adversary. And this is where, so until now we did kind of filtering and we did clipping. So we still have maybe have a global model that it has a light backdoor in it. How do we get rid of that? To destroy the control of the adversary, the best thing is randomness. So we add noise to it. But this noise should be in each round. So it has a parameter t, so that you can measure it. Because if you add too much noise, you destroy the utility. Because the benign ones are also affected by it. But you also want to make the adversary detached from its strategy. This is why you add noise. So does it help? Yes. These are all attacks that we know. And of course, many artificial attacks have been made on the system. These are some numbers, for example, on Reddit data set, on CFAR data set, and also IoT traffic, because we have from our first project lots of data about IoT traffic, and we put malicious IoT traffic and see if we can kind of detect them. So the results are good for each of them, without the defense and with the defense. So we were happy with that. And also regarding the uncarded targeted poisoning, that means destroying because there is no backdoor anymore, you destroy the result. It also works against the untargeted attacks. These are some attacks. Most of them are the so-called model poisoning. They try to attack the model. because that is more important. And the last one, so we had a problem with, the only problem with Flame, at least until that point of time, was that if we make the level of non-IIDness very high, so that means if for example, each client starts to behave completely differently, then we may take some of these clients still as adversarial clients. So that means if a benign client, after several phases, start to have completely different labels that they don't have anything to do with other labels, then we have a problem there. And with DeepSight, we started to, so if you look at the Flame looks into the connections of these neural networks. And here we started to look into the neural network itself. That means to the neurons itself and the connections to it. And this is the output layer. And look into the output layer and see and measure, or at least calculate, something that we call the energy. So which of these output neurons that are connected actually to labels, that are related to labels, which of them for every model update, for every client, what for energy they have. And here we have a different dimensions. Here is a completely different view to the system. We do not look into the weights. We just look into the neurons and weights together. So all these lines that go to one neuron here, you see, for example, the orange one, and this is for the cat one, the labeled cat. And then the assumption that we make here, and that's also a hassle of this problem, that all benign clients have similar number of labels, not labels itself, but number of labels. If there are clients that have too low numbers of labels, then we assume that this is an attack strategy, because the attacker needs to concentrate on certain labels. It cannot concentrate on all labels because the energy comes down. So what is the advantage? Just very fast through it. The red one is, this means that we don't care which labels the clients have, as long as they are in these regions, in these clients. They have kind of high energy, or by calculating some threshold. When they fall into these areas, then it seems that they are benign. Now, when they have, for example, it doesn't matter what kind of labels they have, which in case of Flame, it was not possible. If the labels are completely different, then we have a problem. So here, if there is one label, it could be adversarial. Also, if some of the adversarial samples, weights, they have two labels, for example, and they still come through and fall into these areas, there are further steps in the algorithm that takes care of that. This is at least what we tried to do. So how these energies are calculated of these neurons, it's actually simple. You just use the weights and the offsets, you normalize them. You have a threshold that is experimentally set, and then you calculate this energy for this step of algorithm to see if there are too many of these neurons with, for example, that are higher than this threshold. Then you know that these are good, and if they are too small ones, too few ones that are over this thing, then you know something may be wrong. But if you are interested, you can look into the paper. And the last part is just a note on privacy-preserving aggregation. So if you have, and in the case of Flame, because we measured that, we designed that. What does it mean? It means that when you have the privacy aspect on the server side, think about it. If we encrypt, so you may ask, if you don't want server to see anything, then encrypt everything and send it to the server. All these updates coming from it is encrypted. So the server, the aggregator, cannot see anything because it is strongly encrypted. However, when you want to do defenses on the adversary, because the averaging function is under the server's control, if the server does the averaging and does not see cannot see the updates, it cannot put defenses on the server side. So this is a bit of paradox on here. And as I said, there are ways to prevent that. At least try. Differential privacy would not always work because it has a problem with the utility. And you have to measure always, is that enough noise that I am adding, not to damage the utility. So that's what I say, existing defenses prohibit access to the model updates to investigate backdoors. So the goal was here, can we use the cryptography in a practical way that we all know, and it is there, so that in the case of honest but curious adversary, that means honest but curious, it means that the server does behaves according to the protocol, but the server would not maliciously try to damage all the updates, send it back to the clients to get information from them. So this is a malicious scenario, which is in federated learning. I think this is more artificial aspect, but it has its own justification. But most solutions, they look at the honest and curious server. So what we have done here is that we use the typical secure multi-party computation as we know from cryptography. There is nothing new here. What is happening is that you have the client, the server is, so to say, curious now. We don't want any that updates leak information about the original data. So what we do, every client shares its, so to say, updates into 2 shares. So it's kind of like a secret sharing, and sends it to 2 different aggregators. So A and B. The assumption in any secure multi-party computation, these servers do not collude. They do not work together, because otherwise the whole system is, so to say, done. Now, if you do that, then you can work with it as you are working on encrypted data. You can do all the aggregation on encrypted data, which is not always trivial from the engineering point of view. But at the end, you can indeed learn nothing according to what guarantees secure multi-party computation can give you about the shares. Now, what is the problem with this approach? It is all beautiful. You have beautiful cryptography, and I love it as well. So now, what is the problem is, you see here in this table, we have looked into Reddit for texts, CFAR for pictures, and IoT traffic for IoT anomaly detection. And as you can see, if the number of clients, these numbers are measurements in seconds, as the number of clients increases, then the time for, so S is so to say standard. So you have a defense against poisoning attacks, and you also want to be private. So flame is against poisoning attack. And so we wanted to know if we integrate poisoning defenses into federated learning, what can we do with privacy on the server side? And as you can see, it is not scalable, at least with the numbers that we have. And with the research that we did, maybe in future we have more advances in computation. But in general, this is not that I would, so to say, advise to a set of service providers, because they cannot wait so much for the privacy part if they want to include also security aspects. Okay. So now the last part is just one slide. What is ongoing work? So the ongoing work is currently, from academic point of view, we have a problem that we don't want to leave out the benign clients who all of a sudden behave awkward, if you want to have an interpretation in a real world. If your colleague whom you know for many years, and the next day comes and wants to go for a ballet dance and he has never done it, then you may say, oh, this is a bit awkward. He is now a big fan of ballet after 40 years. This is exactly like this. A client or a set of clients decide to change their behavior. Now, can we capture that? Can not filter it as a malicious one? So one approach, let's see the 2 approaches that I put here, frequency analysis and random distribution, is to transform the weights from one space, that is the vector, to another space and work with the probability distribution over these weights, and or to work with the frequency analysis of these weights. And in that space, we believe, there is no mathematical proof currently for it, we believe that you can differentiate between benign and non-benign much easier, or at least more precise. It encodes more information in that space, or it gives you more information. And in mathematics, people have done that for let's say, for applications in computer science. And another aspect is completely different way, it's a more physical space, is to use hardware-assisted security. This is also what we are strongly following together with Intel. Hardware-assisted security to hide certain computation from the server, so that, and also from the clients, if there are both sides. In that sense, we of course need to trust the hardware, in the sense that the security functionality of hardware is not compromised, but it makes it much more efficient than secure multi-party computation. And you can do a lot of things here. And that concludes my talk. It is just to mention that federated learning at least surprised me. It has a powerful practical applications, and we have been talking to many companies for using it, and also hospitals to do that. In Germany, it is difficult because we have lots of parties who talk a lot but never want to do anything. I'm sorry, no offense. This is a German conference, and we know it. We talk and discuss too much. Sometimes it's very good, but we don't do it. So this is why most of these projects are done with American companies, but also with European companies, that we had to do a lot of, how to say, a lot of negotiation to our sign NDAs to tell them that we really want to do the research. We don't want anything from their data. That is clear. They don't want their data to be leaked, not the customer data. They even don't want that anybody knows that they have vulnerabilities on certain devices of their customers, because that's the reputation problem. And from academic point of view, we are looking into these problems that I was telling you, that are also not interesting for federated learning, but also from any other learning algorithm. With that, thank you for your patience, and I hope I didn't bore you too much.
No, not at all. Thanks, Ahmad. And are there any questions? If yes, please use your hand-raising capabilities of this conference tool, or if you don't know how to do it, just maybe write something briefly into the chat. As long as there is no question, I would like to ask you a question. You looked into very many types of solution. And if you consider private learning, meaning you would like to keep the data you're learning on private from, say, the person training the model. And if you now look at the marvelous cryptographic solutions like fully homomorphic encryption or multi-party computations, or compare this to hardware-based solutions, as you pointed them out in your ongoing work, what would be your estimate? How could we make machine learning more private? Is maybe there some cryptography helping us, or do you think that this all doesn't scale and we have to rely on hardware assumptions?
It depends. This is, of course, a $1 million question. It is nice to formulate, and of course, it hits to the core of the problem. So I have the following answers for you. There are two ways to look at it. From scientific point of view, it is debated among, for example, as you know, among cryptographers. Cryptographers don't want to have trust to any entity. So even not a piece of hardware. On the other hand, from practical point of view, if industry wants to use it, then as we saw, for example, for Apple, they use differential privacy on their servers for privacy, but they didn't use the hardware because then there are two problems here. Expectation goes high. They say you have a trusted hardware on your machine that we cannot you cannot yourself by assumption not accept because we assume that Apple and Amazon and Google, we assume they do not deliberately try to hack into their clients. Yeah, but as we already also saw in what Facebook is doing, what Google is doing, you know, I don't trust any of them. So if they can prove that they have trusted hardware on their machines, and this trusted hardware cannot be hacked by them, so we have a practical solution on the server side. Mm-hmm. On the user side, if you want to run it on the user machines, then we have another problem. User machines, first of all, even if you can do it, there is an efficiency aspect. Second, user may hack into their devices or external parties may hack to devices. If you say, I use trusted hardware, then people come and say, what is with side channel attacks? What is with cache attacks? So these are cache-based attacks. These are the problems that we are concerned with the hardware as well. But in practice, I would say a hardware solution, if people are ready to do it, is more efficient for short term than any sophisticated cryptographic solution. This is my own experience. Just experiencing the practice. From academic point of view, of course, we want to have a nice combination of both, if possible. Until the time where cryptography is, so for example, in the DeepRive project of Intel, Microsoft, and a number of academia in the US and also in Europe, this is the DARPA project. Intel is building a chip for fully homomorphic encryption. Now, if you have this chip, there are some dirty stuff about it. How do you distribute several keys when you have fully homomorphic encryption? How do you deal, because at one place you have to decrypt the data if you have many keys. So even if you have hardware for fully homomorphic encryption, you have other problems, other practical problems to deal with. And we will have maybe one day an extra processor which can do a lot of private computation for us. This is my vision, and I think everybody's in semiconductor industry will think about it, that one day we can do that. However, there are a bit solutions in between. For example, a colleague of mine, Shokan from Water University, they are going to, I think the paper is on our archive, how you can do private machine learning computation by using, so to say, memory, they call it memory tagging. There are some system security aspects that you can use, and it sounded very interesting as a very interesting solution that are combining randomization and hardware-based solutions that are easy, not very, they don't need to have a completely new design. That is what industry doesn't like, completely new design. And we are going to go there. They have to change the way they think how to make chips for us. So to answer the question in a very short thing, cryptography, sophisticated cryptography is not pragmatic for large scale usage. Secure hardware is a good solution in between, but it is not perfect from academic point of view. So I would really, first, a company, I would say, use secure hardware on your server, you can do it. Client secure hardware is not available on all computers. It's not available. Okay, it's available on all mobile phones. You have ARM trust zone, but its usability is very, very, very limited. Yeah.
Mm-hmm. And you mentioned in your talk that there are 2,000 articles on security and privacy for federated machine learning. Isn't this unhandleable? Is there anyone knowing these papers? Can you find them only by searching? And what would you advise young researchers who would like to start in the field to do?
I mean, this is a really, really big problem, because the estimation that we did is what was more than 2,000, because we did a kind of search for federated learning, and then we start to reduce it to scientific articles at all kind of, first on top 4 conferences in security, then on top 4 conferences in security and machine learning, and then we started to expand it a bit, and it is even much more. So from that point of view, it is we try to make it as precise as possible, this estimation. But from what you said, I personally am always very concerned when my students are writing something about federated learning. And weeks I spent with just really annoying them with, did you do enough research about all possible articles? And even if they do it, how can you read so many papers? You just can read the abstract and say, or introduction, they are not doing what I am doing, and hope for the best that there is nobody writing in a footnote exactly the solution idea that you have. So my advice to the students is, maybe this is a bit decadent, but I just tell them, take the last 2 years of every top conference in security, if you are doing security of machine learning, or if you are doing machine learning with security as a sort of byproduct, which is mostly machine learning conferences. There are many of them, but take 2 or 3 top ones and see from this, let's say, 8 conferences in the last 2 years, in your area, let's say federated learning, what is actually published, and then forget about all the related work in those papers. Just read those papers and see, are they doing, are they achieving exactly the results that you believe to be interesting in your research? It's still work, but it's not 2,000, 3,000 papers. But this is a big trend, and we all know, like security was some years ago, and still, and now with machine learning coming, security gets another push, because so many people are interested in attacking machine learning algorithms, which is not a big thing, but it's getting more complex. Yeah.
One last and very short question. Some people are fearing superintelligence or the singularity, and fear that there are existential. What would be your opinion about it? Is there something to it, or is this just nonsense?
I don't know.
Das habe ich
really,
zu viel, Sarah. Existentialrisks. What would be your opinion about? Is there something to it, or ist es just 19 gefunden? Guck mal.
Oh, what was that?
Some superintelligence.
Okay. So what I would say currently, in the all industry projects that we had, where we wanted to solve a more or less engineering problem, rather than, because all people who are doing machine learning, they know feature engineering, this and that, they all know it. But you know, there are cases where machine learning completely the current status, so to say, the current status quo is failing and cannot compete with the human mind. The only thing that we are kind of, I would say, in the practical sense, with the current technology, I would say that is a bit difficult is for human being, the automation aspect. The automation is something that we have the weakness compared to this algorithm. But singularity, you know, let me give me a kind of critical aspect about the singularity. So there is a discussion between, there was a discussion between Elon Musk, Zuckerberg, and some other people. Exactly the people who are really wrong for the society and wrong for being kind of idols, for role models for people, because these are crazy people who got somehow rich, and they are going to destroy our society, and what Facebook is already doing that. So, but when they discussed, there was a tweet fight between them, and I was following that, saying that what these guys have done. And then there was an MIT professor saying that none of these. So Elon Musk was saying, Mark Zuckerberg has no idea about AI, limited understanding of AI, and the professor from MIT was saying all of them don't really understand AI and what AI can do and what it cannot do. It is also a bit strategy behind it to talk about singularity. Maybe one
Ahmad,
day.
I just have to say something. If you have some other talk you would like to attend, the time's up. Please leave and don't waste any time. But I don't know if this is a separate room. You can just finish your argument and, and leave then.
Okay. I don't believe in singularity currently. There is no Skynet, but we have already something like Facebook, which is dangerous enough. Yeah.
Okay. Thanks a lot. Thank you for coming. Thank you for giving us all these insights and these answers. And we are a little behind schedule, and I hope all the other talks will be behind schedule too, and you will be keeping up. And thank you for joining this session, and all the best. Thank you. Bye-bye.